Let's do exploration 2, which reads, assume that e to the x, cosine x, and sine x equal their Maclaurin series for complex numbers as well as for real numbers. And in part 1, we're supposed to find the Maclaurin series for e to the ix. So let's begin by reminding ourselves what the Maclaurin series is going to be for e to the x. And that's going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and that's going to continue. And so if what we want to find is e to the ix, we're just going to do what we've done many times over, which is to substitute in ix every time we see an x. So I'm going to have 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial. And then we want to evaluate these I squareds and I cubes and I to the 4ths, and that's why in the reading just above exploration 2, you were supposed to remind yourselves what the power of i's were. So we're going to have 1 plus ix. I squared is going to give us a negative sign, so we're going to have negative x squared over 2 factorial. I cubed is going to give us a negative I times x cubed over 3 factorial. And I to the 4th is going to give us positive 1. So we're going to have plus x to the 4th over 4 factorial. And that will continue out, but this gives us the basic pattern. So part 2 says, use the result of part 1 and the Maclaurin series for cosine x and sine x to prove that e to the ix is equal to cosine x plus I sine x. Now, I think prove is a little strong. We're just going to show that that's what this is. And we're just going to begin by writing down the Maclaurin series for cosine x, which gives us 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and that continues. And if you notice, this is equal to the real parts of e to the ix. And then the second thing we're going to do is we're going to do I sine x, and we're just going to distribute that I across all of the terms for the Maclaurin series of sine x. So this is going to give us ix minus I x cubed over 3 factorial, and the series continues. And if you notice, that's equal to the imaginary terms of e to the ix. So if we add these two series together, we're going to get all of the pieces. So we do indeed have e to the ix is going to be equal to cosine x plus I sine x. And then we can move on to part 3, which says use Euler's formula to prove that e to the I pi plus 1 is equal to 0. So let's give ourselves a little more room here. And we want to show that e to the I pi plus 1 is equal to 0. Well, we're going to use Euler's formula, which is sitting right here, and use that to expand e to the I pi. And so we can write it as cosine pi plus I sine pi plus 1. And the cosine of pi is going to be -1. The sine of pi is going to be 0, and I'm going to have plus 1, and that's going to be equal to 0, which is what I was supposed to show.